Okay, so we're back. Here's problem 2 from homework 1. Let's read it together. We have experimental data of another particle's movement was measured in another UHART laboratory and was curve fit to find its acceleration can be approximated by the equation A is equal to negative 0.004 v squared. That's with meters per second squared and meters per second. And the particle starts at t equals 0, x is equal to 1200 meters, and v is equal to 800 meters per second. I updated it with that 1200 because I didn't like it. It was giving me negative numbers. I think I did this correctly. So we want we want to find the time when velocity is equal to 10 meters per second and the distance traveled when v equals 10 meters per second. So I don't know for sure that I got this right, by the way. I should full disclosure. I don't remember. I might have adapted a problem from somewhere else, or maybe even just taken it from somewhere else, but I don't quite recall. So let me write down here. I put the basic stuff down at the top of the page. If you please focus. Camera, come on. Why are you doing this to me? Focus. There you go. All right. So let's write down the preliminary stuff here. And okay, so I'll just write that as a particle. I think I spelled it right this time. And it's A minus 0, the acceleration is 0.004 v squared. And we also know that at t equals 0, x is equal to 1200 meters, and v is equal to 80 meters per second. Okay, so our find, so that's the given up above. Sometimes I'll write given at the time, then I'll write find underneath it. Maybe I should here. I'll try to make it look, that's a good thing to do, right? Just go to given this, find A t at, not x, v. V is equal to 10 meters per second. And B, find, now it says when they say distance, what they really should mean here is delta x. Like, okay, so we have to be a little careful sometimes. I don't think it matters in this problem, but sometimes it might like reverse direction sometimes during the period of the thing going on right here. But I don't think that's the case here. But you might have to do a problem where you need to check and see if it changes direction. So if they ask you for the distance, it's to that point where it makes a direction change, and from that direction change to the final position. So you have to, sometimes it'll be like a little tricky that way. So be on the lookout for that. So this first one right here, we know that this is case 3, as we've described it before, and that because acceleration is a function of velocity. Here we want to find time. If that's the case, then we're going to use acceleration is dv dt, right? We'll use that and break it apart and rearrange it to say that dt is equal to 1 over a dv, right? And we can integrate those. And we're going to start at 0 and go to t, and we're going to start at 80 in the velocity and go to v, and that's going to give us a new function that tells us the description of the motion. So this over here, I'm going to move it over to the side over here because right there. I'm just go ahead and say, we know that's going to be t. And here we're going to have a little bit more of a mess going from 80 to v because now we have 1 over, so 1 over our function, negative 0.004 v squared, right? dv. Did I do that right? I think so. Well, I can move this out and do the little math here, and I happen to know that 0.004 where'd you go inverse? There you go. Is 250, right? 1 over 0.004. So we have a negative 250 constant over here. Integral of, and this is v squared, but around this, so it could be v minus 2, taken from 80 to v dv. And that's not a difficult integral to take care of. So we have negative 250 and times, we're going to add 1 to it, right? We're going to add 1 to it, so it'll be negative 1. But we also need to bring that negative 1 out to the side right here. So it's going to be 1 over negative 1, which is just negative 1, right? And then times 1 over v, right? And we need to do that from 80 to v. Those negatives cancel out right there. And maybe I want to write that down separately. Yeah, I'll write it down as a whole new thing. T is equal to 250 over v minus 80. All right. So now we can go ahead, we can actually solve for this thing right here. So we go at v equals 10 meters per second. T is equal to 250 divided by 10 minus 80, which is equal to, wait a minute, that is not true right there. My bad, sorry. This should be 250 divided by 80, which ends up being 3.125. It's difficult to think and talk and write at the same time. One of them gives way. So this is 21.75 seconds. All right, so that's part A. Part B, we want to find the position. So now we're going to do case 3 again here, but now we're going to use our good friend. The acceleration is velocity times dv dx. And we'll rewrite the thing out. Get x over here by itself, and then say velocity divided by a dx. Nope, dv. My bad. dv. Integrate those. And the thing is going to start at, let me see, did I mess everything up here? Yeah, I think so. 1200. Right? Starts at 1200 and goes to x, and then this one starts out at 80 and goes to v. So let's plug in what we know for a. We can go ahead and do this one over to the side. I'll do this over here, x minus 1200. That's all that is right there. And is equal to integral of 80 to v of velocity divided by a negative 0.004 v squared dv. Let's move this guy out to the side because he's a constant. And we know that one of those v's is going to cancel one of these v's. So we have the integral 80 v 1 over v and dv. And we know that's a special case, right? Where it's, when we have 1 over v or 1 over x, integral 1 over x is going to be the natural log, right, of x. It's an identity we should have memorized. It's common enough. So I'll keep writing this out right here over to the side. But now we'll say negative 250 times the natural log of v from 80 to v. And that's going to give me the equation right here of x is equal to, where'd you go, Catman Joe? I guess just negative 250 natural log of v. And then we have, let me double check something here. I want minus, it's going to be minus, so it's going to be plus, all right? But the natural log of 80 times natural log times 250, boom. Yes, that becomes 1,095. All right, so this actually could have been all right. I think I should not have changed this problem with the 1200. Now that I'm thinking about it, that's right. We're not going to hurt anything. So it starts out. So it's going to be plus 95.5. I'll go 5 sig figs there. But then also we need to add in the 1200. So that was my mistake there. It would have been totally fine if I hadn't tried to fix it. Okay, so let's say that this is the final equation right there. So now I got to go. That's 1200. I got to add that together. Boom. And we're going to say that it's a negative 250 times the natural log of v plus 2,295. So we go at v is equal to 10 meters per second, x negative 250 natural log of 10 plus 2295, 96. So we take 10, and the natural log of that is 2.302, thereabouts 250 times that, but this is negative, so we subtract out, and we get 1,720 meters. So those are the answers right there, right? So let's see the answers. And I hope I did it right. We'll say that T is equal to 21.8 seconds. B is going to be, I guess, say delta X is equal to 1,720 meters. And I said, well, how do we know that there's not an inflection point? Well, it's really just a natural log thing. So it's not gonna have like a peak and go to the thing. It's really gonna kind of die out. So one good thing that we can do whenever possible is to graph this stuff. So I actually graphed problem 1 and problem 2 in Excel. You could obviously use something else. But let's say here, okay. And actually I was trying out some things in here, so I could actually do a fresh sheet if I wanted to for my problem 1. And if you'll recall from here that in problem 1, do I want to do this? I guess so. Everything was a function of time, so we just start off with a string of time. And I'm taking a guess and saying I'm going to go quarter-second increments right there, right? And if you start that right there, you can just sort of pull this down once you highlight them. And we went down to trying to see if there was a time. Let's see, what time did we go to? T equals 3 seconds was one of the only things that came out through. Yeah, so we might actually want to go a smaller increment than this. So maybe I want to go I'll go 0.1. It's a little better, 0.2. There you go. And Excel recognizes that you have a pattern right there. So yeah, that'll be pretty good. We're going down to 3 seconds or something like that. And then we go position, velocity, acceleration. We had an equation from that first problem where did we have it? We came up with something. Yeah, we said that it was going to be equal to 2 times this time raised to the 5 halves. So we need to open parentheses, 5 divided by 2, close parentheses, minus 2 times this time right here, squared, yep. And then plus 2 times this time. And then, was it plus 3? I think it was plus 3. Boom. Okay, so when we have that and we have a column next to it, we can just double click on this little corner right there, and that'll give us, let's not make too many sig figs there. All right, there we go. All right. One thing we just confirmed, obviously, that we did plug the numbers in for 3 seconds. We got that 22.17. We did the same thing here for velocity, and the velocity was V is equal to, where'd you go, man? Oh, that's the original one. That's why. 5 times this raised to the open parentheses 3 halves minus 4 times t plus 2. And I think I got that right. Let's see. Let me get rid of some decimal places there. All right. And then lastly, the acceleration is going to be acceleration. Where'd you go? Acceleration. Oh, that was equal to 15 halves times t. Oh, I could have made a square root of the. I could have gone square root sqrt of this, and then plus, or no, minus 4. Minus 4. Sure. And boom. And okay, so one of the things was asking, okay, part A, they wanted to find out the time when A was equal to 0. Well, you could see that it started out negative and then came down, right? So that makes sense that it was somewhere in between the 0.2 and 0.3. Other questions we asked, they wanted to know the velocity when x is equal to 20, right? So you could look at right there, and you can see it's somewhere between 2.8 and 2.9. That's the that's the position, right? So somewhere in between here and here, so you can see that the velocity is going to be somewhere between 14.2 and 15. And what did we get? We got 14.7, so that makes sense. And then we also wanted to add 3 seconds. We were able to get all, these are the same answers that we had before. What, did I just, no, okay. And, you know, we might even want to go ahead and graph these. Now, sometimes you need to make separate graphs because the range of the position of the velocity or the acceleration might be so much that you can't see what the other ones are. But we just highlight those, insert them, and put them right in there so we can kind of see what they look like, right? You kind of get a better sense for the big picture of these things. So you can see, like, okay, here's where it is at 3 seconds, but you can see that there's no inflection points. And we can also see that we probably should have chosen more a finer or smaller time increments right here. Something I wanted to add to the, potentially add, but I didn't, is to tell you to numerically take the derivatives or integrals of these. So, well, what you can do if you wanted to find the acceleration here, all you need to do is take this minus that divided by the time increment, but we could also write it as that. that minus that. And this is a crude approximation, right? And you see that it doesn't come out to the same number. But if you were to, let's see, let me just copy this over to the side over here, right? And I will get rid of that one and keep that one. That's the acceleration. But I want to move this one over to my numerical one right there. And you can see that they're pretty close to each other. If you want to get them even better, what you do instead of this is like this is a backwards cast, right? We're kind of using the previous thing. So what we could do instead is we could do the straddling. I can't remember the names of these, but instead we'll go like that to that right there, right? So we've got to remember though that there's the one at the bottom, that the very last one is going to be bad, but we'll go to this one right here. And so this one is bad because it's actually trying to use cells that aren't there. So we can actually just get rid of that. But you can see that that gets really close. So we've numerically differentiated the velocity to get acceleration. Now you can also do this by finding the integral, right? We could. And remember that the integral is the area. Now, this is going to be a crude one because we're not necessarily going to, we could use some of the other things where like trapezoid rule and that type of thing. But let's just take a very small, we'll just say if we had fine enough increments that this might be okay. So now I want to find, I wanted to integrate the velocity to find my position right there. So let's just take, and I couldn't do it up here, right? I could just say, take that, multiply the velocity by the time increment. But remember, I think, here's the time increment right there. So we're just multiplying that there. Remember that it started at one of the 3, right? So I'm going to add to the cell above, right there, and I'm going to start at 3, right? So now when I go and move this one down, it'll always refer to the cell above it. And this is not going to be any good, so that's good right there. So let me recopy this, and let's just plot the two things that are position, right? This one's position, and that one's position. So we're going to leave that one. I'm going to delete this one, and then I'm going to move this one over to here. And we can see how close we got, right? It's got the same trend, but it's shifted over a little bit, but that's our numerical integration of the velocity to get position. And I think by messing around with these in a graph, it gives you better insight and appreciation as opposed to just plugging numbers in. And that's something that's really common, I think, in all aspects of engineering, is that we can, instead of just coming up with an absolute value of something, you could see the trend of what's taking place. And you could also double check yourself, right, that you haven't made a mistake. Now, I did something similar here. Now, this was kind of a weird one because we didn't have time, increments. So what I did, everything was in terms of velocity. So I made my velocity, or I should say speed, right, incremental. And I went down, I found out that I had to go down pretty far. So where the original thing is given is just negative 0.004 times that velocity squared. So I believe, let's see, one of these is a plot of that. I think this is a plot of it. Yeah. And I started down here because you see this, it gets like really large. In fact, it gets to imaginary right there, right? If we, this is the one this is our answer right there, right? Is that 250 divided by the thing minus 3.125. So, but we divided by 0 right here, we get infinite. So that doesn't really count. And remember, we said that this was experimental data that they've plotted, right? They curve fit to the thing. So it's not necessarily going to be it's not necessarily going to be true all the way through an infinite range. It's only true through the data that they collected. So they must have collected data within a certain margin right there and then curve fit it. And of course, the values would be, there'd be some scatter. So it isn't exactly the equation that they're showing, but it's a good approximation to the thing. And yeah, so this one here is our position. Right there, so and as versus time, yeah, position versus time. We can graph, but you can see that the time is getting smaller and smaller and smaller. So I dragged it all the way down till it hit to 0, down to here, boom, right there. So I could see that position. So and on the graph, it's going to orient just from in order right here, even though we have descending time into this graph. Right in here. And I also kind of took a look at what happened. This is the velocity relationship with respect to time. Okay, that's pretty cool. We can see how it's got a logarithmic type. Did I say that correctly? I think so, right? Yeah, well, I guess position has a logarithmic one, right? There you go. Is the position? No, this is the position. There you go. Yep. And and by the way, we might want to also just for our I didn't mean to put it there, but right there for our own curiosity, we could see what acceleration is with respect to velocity, right? That's what that original one looks like, which is obviously sort of a parabolic relationship of acceleration is a function of velocity. There you go. I had that off by 1. So anyway, you can get some insight. We could look around. We could try that numerical differentiation or numerical integration onto these to kind of see how they're related. But gives you a better feel for what's actually taking place. You can also double check that one issue I mentioned about the distance traveled, that it could go, because this is like really, we might call this straight line motion. It's really just a description of motion along a path. The path could actually be curved or whatever. We're going to get into that, what that actually means in multiple dimensions. But this is just a single dimension, of position and how velocity and acceleration are related to it with time. So that's more information than you needed for your homework. But I think it was worth kind of like introducing it and hopefully do some more problems in addition to these. These aren't the only problems you need to be able to prepare yourself for an exam. So we'll look at some practice problems before the exam and make sure that we're really prepared. So thank you.